So we are looking at fixed parameter algorithms, and so far we saw a number of problems for which we had fixed parameter tractable algorithms, including vertex cover, right, 2 power k, even better 1.4 power k kind of algorithms, cluster vertex deletion, where you want to delete vertices to get a cluster graph. We saw a 3 power k algorithm, but there are better algorithms known. We saw an algorithm for feedback vertex set. Where you want to delete vertices to get an acyclic graph. So you want the subset of vertices to cover cycles, right? We had some naive branching algorithm, and then using this technique of iterative compression, where somebody has given me a k plus 1 size solution, can I take advantage of that? And then we will iterate, and that gave us some, I said 8 power k, but there are much better algorithms known again. And then in your problem sheet, you saw more deheating set. There is something called odd cycle transversal. Here you want the subset of vertices to cover only odd cycles, which means that when you delete this subset of vertices, the remaining graph becomes bipartite, right? So this is a harder problem. I mean, again, it's fixed parameter tractable, but the algorithm is a lot more involved. We are not going to get to it. But in your problem sheet, you saw an FPT algorithm for odd cycle transversal in some special class of graphs, perfect graphs, where life is easier. Okay? But for general graphs, also it is fixed parameter tractable, but it requires more work. And then more, right? You saw some feedback vertex set in tournaments, and if right. And then we saw algorithmic techniques wise branching, kernelization. Here it's an idea. The idea is to pre-process the input to make it something smaller, equivalent, shorter instance. Then you can apply brute force, right? So the idea in polynomial time, you want to get a smaller instance. That was the idea of kernelization. Then we saw iterative compression. And there are more algorithmic techniques, more problems. It's a very rich area. There are a lot of work on FPT algorithms. So today I'm going to just give you a flavor of the hardness notion here. Okay? So what are some problems where you cannot obtain a fixed parameter tractables, and how can we argue this? How do we prove it, right? What's sort of an evidence for it? So, and this is very similar to the NP completeness notion, where we have some NP completeness as an evidence to show that a problem is not polynomial time solvable. We will develop, or I will just give you a flavor of the framework in which we can show certain problems are not fixed parameter tractable. Okay. So So let's go back to NP completeness and say, how do we show some problem is hard, meaning it is unlikely to have a polynomial time algorithm? How do we show that? Yes. So how exactly do we show that my given problem is hard? Every instance of this problem is reducible to some other known hard problem. Is that what it is? It's the other way. Every instance, so we take a known hard problem and say that every instance of that is reducible to my current problem. And what are we trying to say? That if this algorithm has a polynomial time algorithm, then this problem will have a polynomial time algorithm, right? And which we have already shown is unlikely. So this is unlikely. So that's the idea. So this is essentially using an algorithm for this problem as a subroutine to solve a known hard problem, but that's already known to be hard. So I can solve that using this algorithm. Since that is already known to be hard, such an algorithm is unlikely here. So that's the idea, right? So for that, two things we need. We need somebody to give me a starting point, right? Some known hard problem. What is a known hard problem? Where do we start this, right? So that's what Stephen Cook and Levin proved in 1971, 72, that satisfiability problem is NP complete using the notion of Turing machines and NP and all that, right? And then the whole industry started. Now we have thousands of NP complete problems. So in a similar way, here also we need a starting problem where we start from to show some hardness. So one, you need a starting problem. Second, we need a notion of reduction, right? In the case of NP complete problems, the reduction that was useful was polynomial time. Why? Because what we wanted to show, we have a known hard problem. You want to reduce to my current problem. And the reduction was in poly time. That was the restriction on the reduction. And why? Because the consequence we wanted to achieve was if my current problem is easy, so is the known problem. Okay, so let's call this some pi 1 and pi 2. Then this is why the whole definition of NP complete reductions, the reduction is supposed to be polynomial time, because so why, I mean, how do we prove this? If my current problem pi 2 has a polynomial time algorithm, then pi 1 has a polynomial time algorithm. Why? How do you design a polynomial time algorithm for pi 1? Assuming that there is a polynomial time algorithm for pi 2, how do we design, using this reduction, how do we design a polynomial time algorithm for pi 1? So let's first take the input of pi 1, right? Because it's something which I want to solve for pi 1. I'll take that input, reduce it to an equivalent instance of pi 2, apply pi 2's algorithm. Based on that, I get answer to my pi 1 question. Okay. Now everything happens in polynomial time because pi 2 runs in polynomial time and the reduction is polynomial time. Okay. So now let's try and translate this kind of an idea to in the FPT world. Okay. You need a starting problem, I will give you later, but let's think about what kind of reduction we want, right? So here we have some problem pi 1. So remember, it's a parameterized problem we are talking about. So you have an input and a parameter all the time, right? So you have x comma k is what you get. And I want to reduce to some other, my current problem pi 2, so x prime k prime, right? And what sort of consequence do I want? What do I want? Because suppose pi 1 is hard in the parameterized world. What does that mean? That I don't expect an f of k polynomial in an algorithm. Okay, that's what I mean by hard here. Because remember, for us, the notion of easy fixed parameter tractable is because it's a parameterized problem. There is some function of k times a pure polynomial in n. That's what the notion of easy is, right? So what sort of consequence do I want? then so is pi 1. That is what I want. So, if pi 2 is FPT, fixed parameter tractable, right, that is the term for it, equivalent to polynomial time here, which means an f of k input size, then so is pi 1. This is what I want. Now, let us think about what condition the reduction should satisfy to achieve this consequence. So, how much time should I be allowing for the reduction? Right. Ultimately, what do I want? I want pi 2's algorithm as a subroutine to solve pi 1. Right. So, I take an instance of pi 1, convert it to an instance of pi 2, use pi 2's algorithm and get back the algorithm for pi 1. But all of this should happen in fixed parameter tractable time. Now, I am given little more time, not just polynomial time, because I am allowed some f of k in the input size time, right. So, can you tell me what time I should be allowing here for the reduction? FPT time, right. So, I should be allowing myself some f of k times cardinality of x power c time. That is one thing, right. I am allowing a lot more time because overall I wanted to take FPT time. But there is one more condition I need, which is very important. That is always the case, because when you say reduction, you are reducing to an equivalent instance. An equivalent instance means if and only if. This is true if and only, this is S, if and only if this is F. So, that is what equivalent condition is. But what else do I want? So, look at the parameters carefully now, right. So, some FPT algorithm for pi 2 along with the reduction should give me an FPT reduction for FPT algorithm for pi 1. That is what I want. Okay. So, let us take some simple NP complete reduction. We will see what we have a problem, right. So, what do we know? We know that vertex cover is fixed parameter tractable, right. Let me see if I can use that to give a fixed parameter tractable algorithm for some other independent set problem, because independent set you can reduce to vertex cover. Okay. Then we will come back to this reduction thing, right. So, basically in the parameterized world, the reduction should satisfy two conditions different from NP complete reductions. One, you are allowed much more than polynomial time, you are allowed FPT time. Second condition, I am now going to tell you, we will derive what it should be after I do the other example. Okay. So, we will come back to that reduction now. Let me now use, you have this independent set problem where given an input G and K, you want to know whether there is an independent set of size K. Okay. And we know, already we have seen that there is a reduction from this problem to vertex cover. Do you remember the reduction, or how does it work? Can you give a polynomial time reduction from vertex cover to, from independent set to vertex cover? So, what does reduction mean? I should come up with some G prime, K prime, such that G has an independent set of size K if and only if G prime has a vertex cover of size K prime. That is what I want. That is what reduction means. Can you tell me what G prime is, what K prime is? G prime is G, okay, good. And K prime is N minus K, right, where N is the number of vertices in G. Okay, this is a very standard simple reduction that you take an independent set. Now, I want to see whether so this reduction already satisfies the running time, it is only polynomial time. You are even allowed FPT time, so which is nice. Now, can I use the FPT algorithm for vertex cover to design an FPT algorithm for independent set? Because we already know a 2 power k algorithm for vertex cover, remember? So, can I use that and design an FPT algorithm for independent set using this reduction? No, what happened? Why not? So if I want to use an FPT algorithm to design an FPT for independent set, what property do I want on K prime? That's it, right? That's a second condition. So now let's go back here. So from the NP completeness reductions, I need different from NP complete reduction. There are two conditions in my reduction. One is that you are allowed more time, not just polynomial time, you are allowed some FPT time. This is sort of a relaxed thing, but the more constrained thing is that K dash should be a function of K alone. That's it. Any hardness theory, you have a reduction, you have a notion of reduction, you need a starting problem, and then you are all set, right? So let's take, I'll just give you some starting problems. And independent set or is hard in the parameterized world. I'm going to just say which means that no f of k n to the c algorithm likely. And the actual precise notion of hardness here is what is called W hard. Okay? It's like NP had some historical reason, non-deterministic polynomial time. There is something called W which stands for Weft, and that is defined using some circuit theory. But don't worry about all that, because for our purpose, you need a starting problem, you need a notion of reduction. We can start the game on proving hardness. Okay. Now, of course, why is this W hard? I mean, what is the evidence? So, the people who built the theory initially actually had come up with some evidence using some circuit theoretic notions and Turing machines to show that it's hard, but let's not worry about it. Okay. I'll just tell you that it's hard. And we have a notion of reduction. Again, important, in the reduction you are allowed FPT time, but the key thing is that when you reduce, your new parameter should be a function of only the original parameter. It should not get diluted with the input size. It should not have an n there, because in particular, because you can't achieve the consequence which we want, that if this is FPT, that is FPT is what we want. Clear? Okay. So, can we show click is W hard? Given a graph G and an integer k, I want to know whether there is a click of size k. Click to independent set or independent set to click? Because this is my starting problem. I haven't told you click is hard yet. We are trying to prove click is hard. Never confuse the direction in which you want to show during hardness, right? So, we want to reduce independent set to click. Can you reduce it? What do we do? How do we do? Just take the complement. What happens to k? Remains the same. K, you have to pay attention to k, because that is the crucial thing, right? And it's actually polynomial time. You are not even taking advantage of the FPT time you are allowed. Okay? So, this implies immediately that click is W hard. And when I say W hard, you should also remember that it is for this parameter. Parameter is the solution size. Okay, I am looking for a k-sized solution in k-sized independent set or k-sized click in my graph, and that is what is hard. You may change the parameter and do something else, and then problem might become easier. So, when we say this W hard, it is for this parameter, right. So, for example, I should have mentioned this before. Already yesterday we saw that K coloring is unlikely to have f of k n to the c algorithm, right? Because 3 coloring is NP hard. So, if I put 3, this will give me a polynomial time, right? So we know some problems already, but this is even very strong. You can't even have an n to the gk algorithm. You can't even have some n power some function of k algorithm. That is not true for independent set or click, right? Can you give me an n power k algorithm for independent set? Given a graph, I want to know whether there is a k-sized independent set. Try all subsets. Similarly for click. So, they have n power k algorithm. For k coloring, I do not even expect something like a n power k square algorithm, because same reason, put k equal to 3, that gives me a polynomial time algorithm, which is unlikely for 3 coloring. So, this is a stronger notion than W hardness, because I am even disallowing n power gk algorithm, whereas this is disallowing only this kind of algorithm. Okay, so independent set is hard, click is W hard, and so these problems actually, or when we say this para NP hard, parameterized in some sense, simply because even for constant k the problem is NP hard. Okay. That is not true for independent set. If I want a 5 element independent set, I can do it in polynomial time, right? You try all subsets. Okay. So, let me mention one more problem, and then we will do one reduction in this lecture. That is all the plan is. So, say a multicolor independent set. So, what is the problem? My input is G comma V1 union V2 union Vk. My parameter is k, and the question I am interested in is, does there exist an independent set in G that has exactly one vertex from each Vi? Okay. So, think of it as my vertex set is partitioned into k parts. Okay. And now I am also looking for a k-sized independent set, which in general is W hard, we already told you. But I am saying even on this special question where I want an independent set of k size, but it should each should come from each of the Vi's. Such a restricted, so this is called multicolor. Think of each Vi is one color. Okay. So, there are k colored graph we have in a vertex set, and I am looking for an independent set which contains exactly one from each color. Okay. And again, I am not going to prove it, this is also W hard. So, what I am now going to do is just run through a reduction. This will also be an NP complete reduction, but it is even stronger, it will be a parameterized reduction. Now, to show that this problem of dominating set, you know what this problem is? No? Come on, I am sure you would have seen it in NP completeness approximation. No? Not at all? Okay. So, here your input is a graph G, a parameter is k, and what is the dominating set? An S contained in V is a dominating set you know what the definition of dominating set is. Yeah, what is a dominating set? A set of vertices is a dominating set if adjacent to it or neighbor, both are same, no? Exactly. So, in a sense, vertex cover is covering edges, dominating set is covering vertices. Okay? A set is a dominating set if for every V in V, V is in S, or there exists a U adjacent to V such that U is in S. So, a set is a dominating set if you take its neighborhood, it's the entire vertex set. Okay? So, this is again a very important parameter, very well studied, lots of work in the graph theory circle on this problem. So, the question is, does there exist a dominating set of size at most k or exactly k? Okay. So, let us see an example. So, here is a graph. So, what would be a dominating set for this graph? Let us say I pick A, and maybe C. Does A and C dominate everybody? Okay. What is not? E is not dominated, right? Everybody else is dominant. So, let me pick E also. Okay. So, does everyone see this? That you pick any vertex, either it is in the dominating set or one of its neighbors is in the dominating set. So, that is a dominating set. Okay. You see the difference between this and vertex cover, right? Vertex cover is covering edges, dominating set is covering vertices. So, clearly this is not a vertex cover because BD edge is not covered, but this is a dominating set. Okay. So, minimum dominating set, testing for finding a k size dominating set is NP complete. It has some approximation algorithm, it's studied in many paradigms. There is a whole lot of graph. There are books, entire books devoted to dominating set, domination. Okay. There are variations of domination and so on. So, what I am going to do is to prove that dominating set problem is W hard by a reduction from multicolored independent set. And as a bonus, you also get that it is NP complete. The reduction will also tell you it is NP complete. When will a parameterized or reduction be an NP complete reduction also? So, suppose I have this parameterized reduction. When will it be an NP complete reduction also? Exactly, right. So, recall two differences from NP complete reduction for parameterized reduction. You are allowed more time, you are allowed f of k times fpt time, and the k prime should be a function of k. So, k prime be a function of k is fine. If you did not really use the exponential time you are allowed, you only use polynomial time, this will also give you an NP complete reduction if you start from an NP complete problem. Okay, that is also true, right. Of course, in this case the problem we are going to pick is also NP complete, so we will use that. Okay. So, for the rest of the lecture I am going to give a reduction from multicolored independent set to dominating set. I will actually spend only polynomial time, and more importantly, I will make sure that the k goes to k here. Okay. K should be a function of k for the hardness reduction for in the parameterized world. Okay. So, it is a fairly easy reduction. So, it is yeah. Okay. So, what is the input here for multicolored independent set? You are given a G which is colored, and you have a parameter k, and I am looking for an independent set that in G. So, the edges can be everywhere, wherever it is, right, in this graph. I am looking for an independent set that picks exactly one vertex from each of the VI's. And what do I want to get? I want to get some G prime, and it turns out it will be actually k such that G has a multicolored independent set if and only if G prime of size k, if and only if G prime has a dominating set of size k. That is my goal. Yeah, okay. Okay, so now I have to construct G prime, somehow encoding independent set here to a dominating set. So, the construction will go like this. I will take a new page here. So, my G has k different paths, and there are all kinds of edges here, right. This is how G looks like. I am looking for a k size independent set. My G prime will look like the following. I am going to take the same V and add one extra vertex for each of the color classes, let us say C1, C2, Ck, and these vertices are the same of the V1 vertices. I am going to make these guys adjacent to everybody and make this a clique. To start with, okay. What's the confusion? Is there a problem? Yeah. So, I am just starting the construction. I've just started. What is the input to the multicolor independent set problem? You are given k parts, k colors of vertex set, and then some edges. Edges can go across colors, same colors, all kinds of things are given here. That is how the graph is given. This is the input graph for my pi 1 problem, which is the multicolored independent set problem, where I am trying to find a k sized colorful independent set. I am going to convert it to a dominating set instance here, and the dominating set instance has the same, to start with, same vertex set, plus I am going to add some k other extra vertices, one for each color class, and make the Ci adjacent to every vertex in Vi. In addition, I am going to make each Vi a clique. Okay, I am not done, there is more to do, okay, because I have not captured the edges in the graph at all. The graph has edges, I need to capture something like that. So, every edge here, right, which is going, I mean, you can assume that these, yeah, it does not matter, okay. So, any edge which is like some edge E which has some vertex Ui, Uj. So, that means this is coming from the vertex set Vi, this is coming from vertex set Vj. I mean, I ignore the edges within same color class, that's not going to play any role for me. Look at these kind of edges. An edge which has one endpoint in color class I, other endpoint in color class j. I am going to create a vertex for every edge here. Now it's a vertex. There is a vertex for every edge here. And what is its adjacency? Yeah? Or the Vi and Vj. No, that was the adjacency here. But here I am going to change it. What I am going to do is the following. Okay. Okay, why I am doing all this will come when I do the equivalence proof. We will see what it is. So, what I am going to do is make E. So, let us say you have this color class Vi and color class Vj, and I have a vertex for E, and my Ui is sitting here and Uj is sitting here. I am going to make E adjacent to everybody except Ui and Uj. Except Ui and Uj in these two color, just in these color classes, just to these two color. E is an edge which has one endpoint in one color class, another endpoint in another color class. Now, corresponding to that edge, I am going to create a vertex here called E. That vertex will be adjacent to all vertices in these two color classes from which the endpoints are coming, except for the corresponding Ui and Ej. Okay? That is it. That is my end of my construction. So, let us go over it again. If something is not clear, let us see. Ask me. Okay? My construction is that's it. So, what I have done here, I am asking for a multicolored independent set here, and the input here is some k color classes and some edges within, across, all kinds of edges. My G prime, this is my G prime. To start with, we will have the same set of vertices, this V1, V2, V3, Vk. All the vertices of the Vi's. For each color class, I am going to add an additional vertex C1, C2, Ck, and this Ci will be adjacent to all vertices of Vi, and each Vi is made into a clique, and I do that for each color class. And then corresponding to an edge within a color class, I am going to ignore. I do not need it. We can even assume that in this case that each color class is an independent set, because I am looking for a color in independent set, one from each anyway. So, it does not matter what the structure inside is. For any edge which has one endpoint in some color class Vi and another endpoint is in Vj. So, for every edge I will have a corresponding vertex here, and that vertex will be adjacent to these two color classes this edge corresponds to everything except the corresponding Ui and Uj. That is my end of the construction. Now, what do I have to now show? That this is an equivalent instance, right. So, what do I have to show? Claim is G has what? Independent set, not just any independent set, a multicolored independent set of size k if and only if G prime has a dominating set of size k. Okay, so that is what I want to show. So, let us try. So, suppose G has a multicolored independent set. So, that means it picks a vertex here. I can use some other color. Maybe a vertex here, vertex here, vertex here, vertex here. These green vertices together form an independent set, right, a multicolored independent set. Now, I have to produce you a dominating set in G prime, right. So, a natural choice would be the same green vertices. Let's try that. Okay, I'm going to take the same green vertices, and I want to claim that these vertices actually dominate the entire graph in G prime. Okay. Remember, domination means what? Every vertex outside should have a neighbor in this set, right? So let's check that out. So every vertex in this color class is adjacent to this, because I made this the click. So all these vertices are dominated, no problem, because there's one from each color class, so the Ci is dominated, and all the vertices here are dominated. Now I really need to worry about the edge E. What happens? Any edge. These edge vertices should be dominated from whatever I have picked, right? So let's look at some edge E, and suppose it is not dominated. Okay, what does that mean? Let's say it is coming, the edge has endpoints in color class V2 and Vk. Okay, so why is it not dominated? Because E is not, so let's say E is some u comma v, right? Why is E not dominated by whatever the green vertices? Maybe the E is not adjacent to the green vertices you picked from both of them, right? So maybe this was u, maybe this was v, and the way we really constructed our graph, remember we made sure that this edge is not adjacent to u and not adjacent to v, right? That's so maybe so whatever you picked from the color class is not dominating E. Can that happen? Why not? Because if that happens, that means that u and v are adjacent, because that's why this was not adjacent to it. But we picked an independent set from here, so the green vertices are not adjacent here at all, and so every edge will have at least one endpoint not picked, not one adjacent vertex picked in the appropriate color class. That's the end of the forward direction. Is that clear? Shall I go over it again? Yes? Okay. So I picked this green vertices, which is the color class, one from each. Multicolored independent set, right? The important property here is that this is an independent set. And my claim now is that I take the same green vertices, they actually dominate this entire graph. Remember, this graph contains these kind of vertices plus these kind of edge vertices for every edge in the graph G. So clearly these green vertices color all these vertices, no problem, because I've constructed my adjacencies appropriately like that. Now suppose an edge vertex is not dominated, which means what? Let's say this edge is some ui uj. Then the way I constructed it is not adjacent to ui and uj, and everything else it is adjacent. So the only way E will not be dominated is that in your green vertex, ui was one of the green vertices and uj was one of the green vertices. But if ui and uj were green vertices, they were adjacent here, because that's what E was ui uj, but I picked an independent set here. So these green vertices dominate the entire G prime. There are k of them. Now that's the forward direction. Let's do the backward direction. Okay. Suppose I have some k vertices that dominate the entire vertex set here. Let's come to C1. Who will dominate C1? Who will dominate C1? Either C1 or a vertex from V1. Okay. Now, if my k size dominating set picked C1, why is it picking C1? C1 is not playing any big role. Instead, I can swap it with some vertex from V1. I will not lose any generality. It will continue to be a dominating set of the same size. So, first thing, if your dominating set picked any of the Ci's, let me swap it and pick one from this color class. Now, each Ci needs one from each of the color class. So now I have picked some k vertices from one each from each of the color class. Now I want to claim that that set of k vertices in the dominating set correspond to an independent set here, because I've got a multicolored set here. And why is it an independent set? The same reason this k vertices dominate the edge vertices. That means that if it is not independent, if you have an edge ij, then the corresponding edge would not have been dominated by whatever green vertices you picked here. Okay, so it's more or less the same forward direction proof can be pushed back for the reverse direction as well. Yeah. What is the use of CIs? Yeah, to ensure that you pick somebody from this color class, because remember these VIs are also adjacent to some E vertices, all kinds of vertices, right? How can I be sure that one vertex from this color class is picked in the solution? You can say, oh, to dominate these vertices, don't I need a vertex from here? No, the E vertices also dominate them, right? So maybe you don't even need CI, it just makes the proof simpler. But in particular, I wouldn't know how to argue that each VI is a clique. You can pick is a different story. You are given a dominating set. You have to argue that that dominating set would necessarily pick something from Xi. You are not constructing a dominating set. You are given a dominating set. I am trying to argue about the dominating set. So, to argue that in that dominating set there must be somebody from VI. You are not picking a dominating set. What is the converse direction? The converse direction is that suppose there is a dominating set of size k for G prime. I don't know how it will be. So you can't say it will be from each color class or something. Right? This is important in the proof. You are picking an arbitrary, somebody has given you a dominating set and I am trying to construct an independent set. Now, I don't know that dominating set how it will look like. I have to argue. So, for that proof, to ensure that there is somebody from each dominating set, each color class, I just add this guard vertex Ci, because I know that Ci has to be dominated and nobody else is dominating Ci. See, these vertices are dominated by some of the E vertices as well. So it makes the proof harder. Okay, good. So we have only spent polynomial time because we really didn't exploit the power of exponential, because what did we do? We added the CIs, and for every edge we added these edges. These are all some, in square kind of running time is what I have spent. So this is also an NP complete reduction. This is a parameterized reduction because the K went to K, which is important. Okay. So let's do one more reduction. I just thought of now. Okay, so given let's look at the non-graph problem for a change. Given a CNF formula F, right, given a CNF formula F and an integer K, the question is, does there exist a satisfying assignment we saw this problem yesterday actually with at most K ones. Remember this problem? We looked at it in the context of branching algorithm. Okay. We actually showed it fixed parameter tractable for some special case. What is the special case? Or remember how the algorithm went? It was branching, right? So you want an assignment. So your formula looks like x1 or x3 or x4 bar and x2 or x7 or x6, and something like this. That's our formula. And I want a satisfying assignment which should set at most k variables to 1. Okay. So, a brute force thing would be try all possible n choose k assignments and check whether it is true, and we actually came up with an FPT algorithm for this problem using branching. What did we do? We branched. What did we branch on? So, we picked a clause and said one of the variables must necessarily be set to true, and I will try one by one. Remember that? So, we tried it on 2 CNF sat, but it was not completely that. There was a little more trick to it, because if the variable is like x or y, then you set x to 1 or y to 1, then k drops by 1 in each time. But if the variable is x or y bar, then you have to set x to 1 or y to 0, and you had a problem. K did not drop. So, how did we handle that? Okay. How did we handle that? We said look for a clause which has only positive literals, then branch. There you know k will drop by 1 at each branch, and when you reach a stage where every clause had only some negative literal, not all positive, set all of them to 0. This was the algorithm we had, an FPT algorithm. Depth k, what was the branching factor? Size of each clause. So, if we are talking about a 2 CNF sat or 3 CNF sat or D CNF sat, it will be like a d power k algorithm. But here I am talking about a formula where the size is unbounded. No bound on the length of the satisfying length of each clause. Okay? And here I am asking for, is there an assignment that is setting at most weight k once and satisfy everything. Do you see the difference? When the sizes are bounded, it is FPT, very simple branching algorithm. When the sizes are unbounded, I want to show it as W hard. Okay? When the clause sizes are unbounded. So, we want to show W hard. What does that mean? What do we do? What is the template? We reduce from some known hard problem to this in a parameterized way. Okay. What are the problems I have told you? Clique, independent set, multicolored clique, and dominating set. Right. Let us try and reduce from dominating set. Okay. It is very easy actually if you think about it. Can you encode dominating set like a formula? Just think about what is it we are looking for in the dominating set, and then the formula will naturally fall in place, and then you know that a weight k satisfying assignment would correspond to a k size dominating set. Okay. So, what is it you want in a dominating set? So, we want to reduce dominating set which has the input g k, and I want to reduce to a formula with some CNF formula f k, right. Usually this kind of formula thing is very useful because it is very generic, and if you think very logically about the definition of a dominating set, the formula will naturally fall in place. So, let us write what is it I want in a dominating set. Okay. So, naturally what are the variables? You can think of the vertices will become variables. Okay. So, you had some vertex set V here, let us call it some x1, x2, xn, and here my variables set would be the same x1, x2, xn. Okay. You want to call differentiated by V1, V2, Vn. The variable set will be x1, x2, xn. Let's write dominating set in some logical statement. Okay. So, what do I want? For all Vi, for every vertex, yeah, so that is also a natural thing. Xi is 1 if it belongs to the dominating set. Okay. So, now I am just saying write the definition of dominating set in a logical language. Okay. For all Vi, either Xi is 1 or one of its neighbors x should be 1. Can you say it in logical language using there exists for all kind of statement? Okay. Yeah, logical. There exists an or and. Huh? Yeah. So or yeah, union is are more or here, Boolean or, right? Or of j in neighborhood of I xj. This is what I want. For every vertex Vi, either xi should be 1, the vertex is in the dominating set, or one of its neighbors x value should be 1. Right? Can you now expand it out and write in full conjunctive normal form basically? Right. So, it will be whole and I equal to 1 to n xi or of j in neighborhood of I xj. Right. So, it's and of n different clauses. So, first class will say x1, let us say vertex 1 has 3, 7 and 8 as neighbors. The first clause will say x1 or x3 or x7 or x8. The second clause will say and of x2 or whatever x2's neighbors are, or that, and of all that. It's a huge formula, and of R's. That's the formula. That's it. So, you just translate your dominating set definition into some logically and you will get this formula. So, what I have is that if I call this as formula F, then G has a dominating set of size k if and only if this formula F has a satisfying assignment size at most k with at most k ones. And how do you prove this? Go to your graph. Suppose it has a k vertex dominating set. Go and set the corresponding variables to 1. It will satisfy all these clauses because of the definition of dominating set. For every clause, either the vertex or one of its neighbors is set to 1. Conversely, if you have a satisfying assignment for this with at most k different ones, take the variables which are set to 1 into your set of vertices here in your graph. They will form a dominating set because each clause exactly encodes the definition of dominating set. And note that this is a monotone formula. There are no negations. So, it is a restricted formula, and what we have shown is even here the problem is hard. Right? Whenever you show hardness and if you do it for some restricted thing, it is a stronger result because you are saying that even with this assumption it is hard. So, the general one will be still harder. Right? So, we have shown this, that it is W hard when the class sizes are unbounded, and let us come back to the dominating set problem here. Suppose I tell you that, okay, so in general, we have shown by reduction from multicolored independent set, the W dominating set is hard. Suppose the graph has bounded degree. Suppose every vertex has degree bounded by 10. Okay, you have a graph on, yeah, so I have a graph on n vertices, but each vertex is degree bounded by 10. Now I want to check, is there a dominating set of size at most k? Okay. The general version is W hard. I just showed you from a reduction from independent set. But what can you say about this special version? Why? Exactly. See, now this reduction actually gives you an FPT algorithm, because you take this dominating set, encode it into this CNF clause thing. Now, since the degree is bounded by 10, your clause size would be bounded by, no, 11, because it's xi or one of its neighbors. So, it's bounded by 11, and if thing is bounded by a constant, we know how to do by doing this branching algorithm, picking up the monotone clauses branch, so that gives you a d power k algorithm. Right? Another way, you don't have to even do this reduction if you want to think about it directly. So, I have a vertex. Who is going to dominate it? Who can dominate it? That vertex or one of its 10 neighbors. So, try them all. This is the branching algorithm, right? There are 11 choices. So, take one vertex, delete it, recurse, take another. Exactly, I mean, this is how you will do even for your SAT formula branching also. It is the same thing, right? Okay. And notice that you also have a kernel, right? Let's so dominating set with degree bounded by, maximum degree bounded by d has an O star d power k algorithm. By branching or reducing to DSCNF weight k problem. I want to design a kernel for the dominating set problem when, okay, first of all, can we have a kernel for dominating set problem for the more general dominating set problem? So, given a graph G where I am interested in testing whether there is a k size dominating set, that is a problem. Okay. Now, my question 1, no bound on the degree or any such thing, the more general graph. Is it possible to get some f of k kernel? Kernel, remember, means that in polynomial time, I will produce an equivalent instance whose size is a function of k. Why not? What's the problem? I mean, what if there is a kernel? So, I am saying take the dominating set problem, your graph G, and you are interested in the k size dominating set. Let us recall our definition of a kernel. Kernel means that you are allowed only polynomial time, not FPT time, but you do not have to solve the problem. Just produce me an equivalent instance G prime. Equivalent always means S if and only if S kind of thing, with G prime k prime, but the size of G prime is only some function of k. Yeah. So, what is your answer? We can get a kernel or not? Are you saying you can get a kernel? Okay, he is saying no, you are saying no. Why not?
If it is possible, we have given the algorithm here.
we will get an FPT algorithm. Why? Because you take your GK, spend polynomial time, you get a G prime K prime. If G prime size is only f of k thing, apply some brute force algorithm, try and choose k kind of an algorithm. There is no n, there is only some function of k. So the whole thing would be solvable in f of k n to the c time, but we already showed it's W hard, that dominating set does not, you don't expect to have. So W hard problems don't, basically kernel, if you have a kernel, it is also fixed parameter tractable, right? I forgot to mention this. If you have a problem which is kernelizable, then it is immediately fixed parameter tractable, because you just kernelize it, apply some brute force algorithm. The beauty is actually the converse is also true, that's for some other day, that if it is fixed parameter tractable, it is also kernelizable by some bookkeeping argument. So a W hard problem, you don't expect a kernel of any size, because if you get a kernel, you can make it FPT. But now what I am saying is, suppose you are talking about a graph which has bounded degree, then it is fixed parameter tractable because of this kind of an algorithm. So so can you get a kernel? How do you get a kernel? Include all the isolated vertices in the solution, because they need to dominate themselves. They are the only ones who can dominate. Yeah, what else? If you have a vertex of degree 1, then include its neighbor, okay. Okay, so good. I mean, starting in, my expectation is even much simpler than that. But one difference between dominating set and vertex cover is that following. In vertex cover, suppose I decide to include a vertex into the solution. Okay, you can delete that vertex and work on the remaining graph. Can I do it here? No. Why not? Because, right, so suppose I have this graph and say I decide I am going to include it in the solution because maybe it is forced, it is a neighbor of degree 1, so I am going to force it and include it. Now can I just delete it from the graph and work on the remaining graph? Yes? What's the problem? Now I say, okay, recursively go and look for a dominating set of size k minus 1 in the remaining graph. That's not correct. Why not? Okay, let me repeat what I'm saying. So I have this graph where I'm trying to find a dominating set. For some reason, you decided this vertex must be in the solution. So I just say delete it and delete the edges incident on them as usual. Go to the remaining graph and look for a smaller size dominating set. The remaining problem is not the same as the original problem. Why? Exactly. So for example, if I delete this vertex, look at its neighbors. They are already dominated by this vertex. So in the remaining graph, you don't need to worry about dominating this neighbors of this vertex, which is an information you have to capture and transfer. Because if you just delete the neighbors is another idea. Okay, what's the problem with that? Yes, that's another idea. Okay, take this vertex, go to its neighbors. Okay, the neighbors have been dominated, so delete them also and then work on the remaining graph. That's an idea, okay, but there's some little problem with that too. See, these neighbors may be useful to dominate somebody else. You have denied that opportunity by deleting their neighbors, right? Because yes, they are dominated, but you can use them. Maybe they have very high degree that you may include it to dominate a whole lot of vertices, but by deleting it, you lost that opportunity, right? So let's say, for example, suppose this is a graph, okay, and you say, okay, This is degree 1, I am not going to pick it, so I am going to pick this vertex to dominate, and this vertex is already dominated, so I delete that also. Ooh, then the remaining graph needs a lot more dominating set, but if you keep it, that is useful to dominate. Okay. But if you just delete this, in this example it is okay, but the fact that you do not need to, okay, I am using pointing it here, that you do not need to dominate this vertex because it has already been dominated should be captured in the graph, because the recursive problem is not the same as the original problem, because there are some special vertices who do not need to be dominated. So, but there are ways to handle it by using some coloring terminology. Okay. So, you can say in my graph I do not want to dominate there are some vertices which are colored green or something, and so just dominate the remaining non-green vertices kind of thing. So, that is use the green vertices to dominate others if you need, but green vertices do not need to be dominated. So, you can use some coloring and do all that. Okay. So, coming back to my question of bounded degree graphs, and I want to find a dominating set of size k and I want to get a kernel. Okay. At least you got the correct idea that kernel means I need to do some pre-processing, I need to come up with some rules, in isolated vertices, degree 1 vertices, all that is fine. But here is a very simple observation, right. Suppose if G has greater than k d vertices, what can you say? I am looking for k vertices to dominate the entire all vertices, right, or so not even k d or k plus 1 d, no, k times d plus 1. One vertex can dominate how many vertices? And including itself d plus 1. One vertex can dominate at most d plus 1 vertices, and you are giving me a budget of k vertices to dominate everybody. So, together they can only dominate k into d plus 1 vertices. So, if the graph has more than k into d plus 1 vertices, I will say it is a no instance, otherwise I am done. I have a kernel with k into d plus 1 vertices, right. So, otherwise my resulting graph is at most k into d plus 1. So, it is just there is no n, it is a function of k and d. That is a kernel. Kernel means what? You just want it to be a function of k and whatever parameters in the graph, which is d here for me. Okay, I think I will stop here. Just to summarize, there is this notion of hardness, independent set, click, multicolored independent sets are hard, and we used multicolored independent set to prove dominating set is NP hard. Use that to show that in a CNF formula, finding a weight k satisfying assignment is W hard, even though if the clause sizes are bounded, it is FPT, and there are a lot more problems which are W hard. And you have this notion of reduction, which allows FPT time, but there is a restriction that the parameter k prime which you obtain should be a function of the original k. Okay. So, you need a reduction, you need a starting problem, and then you are ready to do your reduction and prove hardness. So, we have seen some examples, and this is important. Parameter is your choice. In these hardness examples I gave, I was talking about click is W hard under the solution size as a parameter. You change the parameter to something else, it may become FPT. Okay. That is what makes this whole area rich, because the same problem you can look at using multiple parameterization.